Everyone. Today we're going to talk a little bit about limits and continuity. And now limits and continuity can be a bit of an abstract concept, but I'm hoping we can break it down a little bit just to get that basic understanding that will just help with your calculus knowledge a little bit. Now, a limit is what we use to describe the behavior of a function, right? So what I mean by that is it's not necessarily the value of the function at that point, but if let's say you had like a hybrid function of some kind, or you looked at something like a hyperbola, we want to look at how that function behaves coming in from the left and coming in from the right. And the way that we write this, which is if you have done first principles already, you should be familiar with, but we would say our limit as x approaches, and usually we would just use something like a or h, but you might give it a number. In this case, I'm going to give it the number 3, and we apply that to a given function. And so what this is saying is, well, as x approaches 3, this function here approaches this value. And so sometimes we want to split that up from the left and right, which we will do a little bit today. Now, when it comes to just evaluating some very basic limits, we need to do one of the following, okay? We can either substitute in the given value if possible, or we can inspect the graph if that's given to us as well. So this limit here, if I was to try and evaluate that one, I'm just going to substitute in x is equal to 3. And we know that if we were to sketch 3x squared, that at x equals 3, that y coordinate is 27. And so if I'm approaching x equals 3, I'm going to be approaching y equals 27. Now, sometimes it's going to look like you can't apply a limit. And now this should say x approaching 5. My apologies there. But if I was to apply x equals 5 to this fraction here, we know that that's just not possible, right? That would leave us with an undefined function. So if possible, you need to factorize your limits first, right? So I'm going to take the limit as x approaches 5, but I'm going to factorize my function first. Okay, now that bottom one there is a dot, and so I've got x plus 5, x minus 5, and I can cancel those out. So now I'm left with the limit as x approaches 5 of x minus 2 over x plus 5, which we can work with. If I now substitute in x is equal to 5, I'm left with 3 over 10. So as x approaches 5 on this function here, I'm approaching y equals 3 over 10. Now, for the sake of differentiating and this idea of continuity, we need to determine if a limit actually exists, okay? And now what we do in that case is we approach our function, or that point on our function, from the left and the right-hand side. So if we're approaching from the right-hand side, we're approaching from that positive x side, right? And so we represent that using our little plus there on the number, okay? So if, let's say, we were approaching 3, we would be writing that as x3 with a little plus, and then f of x. If we are approaching from the left-hand side, that is your negative x, right? And so we use that little minus there to represent that. Now, if our limits approaching from the left and the right-hand side are not equal, then the limit's actually said not to exist. And this is really, really important when we decide what can be differentiated and what cannot be. Okay, so our limit f of x exists if our limit as x approaches whatever value we choose from the right-hand side is equal to if we approach it. Sorry there. But if we approach that from the left-hand side, okay, so that's when your limit actually exists. And now this idea of a limit existing is super important to this idea of continuity, because a function cannot be continuous if the limit does not exist, okay? Now, a function is actually just said to be continuous if the limit exists at that point, okay? So there'll be parts where your function is continuous, and then there'll be part of your functions where it is not continuous. Okay, and your idea is to kind of decide, well, where is this function actually continuous? Sometimes it is going to be really obvious. So if I've had a look at this function here, we can see that we've got this coordinate here, and then we've also got this coordinate here that opens up at that function there. Okay, so at this point here, we have this coordinate 1, 2, which is actually not a part of our function, and we're saying that the coordinate that is part of that function is 1, 3. So the value of x for which we have discontinuity is x equals 1, okay? And we can use limits to describe this if we like. And so if we were to take our limit as x approaches 1 from the positive of our f of x, we can see that we would end up at 2 if we were to approach, okay? Because remember, we're talking about not at the point specifically, but as we're approaching that point. And now if I take the limit from the right-hand side, I've written that so poorly, sorry. But if I take that limit from the left-hand side, apologies, we are also going to get to 2, right? Because that's what we're approaching. We're approaching this point here. The problem with this function here and it not being continuous is this other condition here, that is that they are both equal to if I subbed in the value into f of a. And what we can see here, because of that jump, is that f of 1 is actually equal to 3. So we're discontinuous at x equals 1 because f of 1 is not equal to my limits, right? And so even though the limits can be the same on both sides, having a jump like that, changing my f of a at that point actually results in it not being continuous. Now, feel free to have a go at this one here by yourself, but I'll go through it again as well, because like I said, continuity and limits can be quite a little abstract concept. Now, this one here, we can see there are 2 points where we're going to be discontinuous, and it's here and here that we want to investigate, okay? So I'm going to start with our x is equal to -1, okay? And I'm going to start by evaluating those limits. So I'm going to find out, well, what happens when I approach x equals -1 from the left-hand side of my function here. And I can see that that coordinate is 1 or -1, 2. So my limit as I approach from that negative side, from that left-hand side, is 2. If I take my limit as we approach from the positive side, I can see I'm going to follow this all the way down to -infinity because of that asymptote there. And so we can say that limit there is equal to -infinity. And so because our limits from both sides are not equal, we have to say that this function is not continuous at that point. X is equal to -1, okay? Because those limits are not equal to each other. Now let's consider what happens here when x is equal to +1, right? So when x is equal to +1, if I take that limit approaching from the left-hand side, I can see that my limit as I approach that is going to hit that coordinate 1, 2. Okay, so my limit as I approach from the negative side is 2. If I take my limit as I am approaching from the positive side, I can see that my coordinate here is 1, 3. Okay? The other thing to keep in mind is that f of 1 is equal to 2 due to that coloured in circle. Okay, so we have 2 rules here that are broken. The first one is that our limits from both sides are not equal. Okay, so we can write that out, right? We can say our limit as we approach 1 from the negative side is not equal to when we approach from the positive side, right? And then the other thing is that our f of 1 is not equal to our limit as it's coming in from the positive side. Okay, so we've got 2 rules there that were actually broken at x equals 1. Now, all this talk of continuity the main reason we want to apply this is to decide if a function is differentiable, okay? Condition number 1 is that it's continuous at the point that you're trying to differentiate. Okay, so if you have one of those weird jumps, you cannot differentiate your function at that point. The other one is that you can draw a tangent line at the point x equals a, okay? And something really important to consider here is we cannot draw a tangent at a cusp or an end point, okay? So let's have a look at this first function here. Can we differentiate at this point a? Okay, and the answer here is yes. All right, we can see that at that point a, we are continuous because our limits coming from both sides are going to be equal, right? Even though we're bypassing that little open circle, the point A is not on that open circle, and so we're actually still approaching that value there. The other thing I can see is if I take both of those limits, they are going to be equal to if I subbed in the value A, okay? Very similar for this next one here. I can see that it's continuous and that limit approaching from both sides is going to be equal to if I subbed the value A in. Now for this third one, we can see very clearly it's not going to be differentiable. And the reason for that is that our limits are not going to be equal to f of a. And that's because we very clearly can see here that f of a does not exist, right? And that's one of our conditions for having a continuous function. And now the last one here is a little bit trickier because we can see that if we take our limits from both points, that we are going to end up at the same point, right? If I take my limit from the left and the right, they will be equal. I can also see that I would have an f of a here. However, we cannot differentiate this due to there being a cusp, right? And what that means is that it's not a stationary point. It's slightly different in that the gradient changes too substantially at that point. And you can't take that gradient at that cusp, right? It almost acts like an endpoint for that function, okay? So because of that, we can't draw our tangent, and therefore we cannot differentiate that function at a. We could differentiate it at any other point, just not at x equals a.